ladies and gentlemen, class recording has started. So, the last thing I asked you to do was explain the differences between atomic mass and average atomic mass. What did you guys come up with in your little small person group discussions? The difference between mass number and atomic mass is a lot easier than the difference between atomic mass and average atomic mass. So, what did we say that atomic mass was? We just sort of described that. What does atomic mass tell us? Christine, go ahead.
The size of an atom relative to carbon-12.
The size of an atom relative to carbon-12, okay? And that's what atomic mass is. But when we talk about, let's say, chlorine, are all chlorine atoms the same? We have these things called what out there in nature? Isotopes, right? So we can compare each individual isotope to carbon-12, but when we go to compare chlorine to carbon-12, which chlorine are we talking about? And that's what average atomic mass takes into account. Okay? So I'm going to start off where am I going to start with you guys today? I am going to start not here. I'm going to start here. Okay? So, this is where we left off on Friday, is that correct?
Yeah.
All right. On Friday, we talked about this sample of bromine that shows up on the back of your outline. And if we look at a random sample of the atoms of bromine in this container, right, we would find that if we looked at 8 of them, 4 out of those 8 atoms turn out to be bromine 79. And that the other 4 atoms out of this random 8 atom sample turn out to be bromine 81. So the fact that I call something bromine 79, we can tell some things about it, right? And I think we did this right at the end of class on Friday, is that correct? So the fact that we have bromine 79, that tells us that that atom is going to have 35 protons, right? And then 44 neutrons, okay? And that bromine 81 has 35 protons, but it has 46 neutrons, okay? What we find out is that this random sample of 8 atoms of bromine is actually pretty representative of what bromine is like out there in nature. About half of the bromine atoms that we find out there in nature are bromine 79 atoms. They contain 35 protons and 44 neutrons. But the other half of bromine atoms that are out there are this isotope of bromine that contain 35 protons and 46 neutrons. So when we say, oh, we have a sample of bromine, what we really have is a sample that is about a 50-50 mixture of these bromine atoms and these bromine atoms. Okay? And separating them is very difficult. So we have to take into account that if we take any random sample of bromine, we're going to have about half of these and half of these. So we need to take an average. If we take an average of the mass number of these 8 atoms, what are you going to get? 80, right? We talked about that right at the end of class on Friday, right? That, we could do one of 2 ways. Either we add up the mass number of all 8 of these atoms and divide by 8, okay? Or we just look at the fact that half of them are 79, half of them are 81, so where's the average going to be? Right in the middle, right? So that the average mass number of bromine is 80. Is that good? But not all elements turn out nice and even like that. For example, let's take a look at this random sample of chlorine. Chlorine's a gas at room temperature, so we put it inside this container. And inside this container there are tons and tons and tons of chlorine atoms. But if we look at a random sample of 8 chlorine atoms, what we would find is that 1, 2, 3, 4, 5, 6 of them are chlorine 35. But then only 2 of them are chlorine 37. Okay? So, if we want to take the average of these two to find out the average for chlorine, can we just say that the average in this case is going to be 36? Right? We can't, because there's more 35s than 37s. So, in this case, because the distribution is 3/4 to 1/4, right? Do we see that the average mass number here is going to be 35.5? Does that make sense where I got that number from? Do you want me to do the math or? Okay. So the average in this case is 35.5 as far as the mass number goes. Now, Maura, can we have a mass number of 35.5?
No, it has to be more.
It has to be a whole number. So, does this represent any one specific atom of chlorine?
No.
No. Or one, it doesn't represent any specific isotope of chlorine. It represents what we get on average if we take some random sample of chlorine. Because we have a mixture of these two, right? But there's more chlorine 35s than there are chlorine 37s. So the average comes out closer to 35, even though that doesn't represent any specific isotope of chlorine. Does that make sense?
So you're allowed to have it even though it's not random?
Because in this case, this is not a mass number, this is an average mass number. And the reason why it doesn't come out that way is because we have an uneven distribution of this isotope and that isotope. Does that make sense? So in this case, when we're dealing with the average, that's okay. Now, what we do on a periodic table isn't average mass number, it's average atomic mass. Okay? So let's take that one step further. Okay? We did this, right, on the front side, is that correct? I think we filled out this part. This part's on the front side, yes? All right, so the average atomic mass takes into account the distribution of those isotopes and the atomic mass of each one. Okay? So, if we go back to this table that's on the back side of your outline, or not, if we go to this table that's on the back side of your outline, we have some actual data related to these chlorine isotopes. Okay? So, here's chlorine 35 up on the top. Its atomic mass is this number. Okay? First, before we get into calculating the average atomic mass, I want you to discuss in your small groups, what does that number mean? The fact that chlorine 35 has an atomic mass of 34.96885. What does that mean? Discuss, small groups, go.
It's comparing carbon 12. It's like no, that is the atomic mass. Yeah, that is. Yeah.
And since all of the thingies are different, they're not exactly like 35.
Okay, so let's discuss it together here. Okay? So, Kate, just because I heard you guys talking, okay? What is the fact that the atomic mass of chlorine 35 is this number? What does that tell you?
Well, you're comparing it to carbon 12, so it's about like 3 times, like not exactly 3 times.
Good. It's not exactly 3 times bigger than carbon 12. If it was exactly 3 times bigger than carbon-12, what would its atomic mass be? Be 36. We're a little short of 36 here, right? But if we look at chlorine-37, right, what are you seeing about its atomic mass in relation to carbon-12? While chlorine, go ahead, Christine.
It's a little bit over 3 times.
It's a little bit over 3 times as big as carbon-12, okay? So we definitely have 2 atoms here. But the important part now in determining the average is this section over on the side, right? The abundance. Like we saw in that random sample of chlorine gas that we saw in the last picture, sorry, approximately what percentage of those atoms are chlorine-35? 6 out of the 8 of them are chlorine-35, so what percentage is that? 75%. And what we find out is that out there in the real world, about 75.53% of the atoms of chlorine that exist are chlorine-35. And then close to 25% of them are chlorine-37. So we have to take that into account when we're calculating the average atomic mass. And this is how we do it. Nope. Nope. Here. All right. Let me change something real quick. I wanted to change this before. All right. Instead of just saying mass, I'm going to say atomic mass. And then I'm going to close this. It's going to say atomic mass. There we go. All right. So we take the atomic mass of that isotope, and then we multiply it by a fraction, where abundance is on the top and 100 is on the bottom. Okay? All we're doing here is taking our percentages and turning them into fractions. That's all. Okay? And then that gives us how much does this isotope specifically contribute to the overall average. We take and we do this calculation for all of the isotopes, and when we're done, we add them together, right? The sum of all of those contributions gives us the average atomic mass. So we do this calculation for all of the isotopes that exist for that element, and then when we add them all together, we get the average atomic mass. Maura, go ahead.
For like chlorine, how there were only 2
Yep.
isotopes, does every element only have 2 or
No, we'll do that in a second. So, okay. Actually, Maura, take a look at the bottom of your outline there. Okay? Yeah, so I won't make you do that one right now. Just, yeah. All right, so with that being said, let's go back here. So, Maura, like you said, chlorine only has how many isotopes? Just 2, so we only have to do this calculation twice. All right, so let's go here. Okay? For chlorine-35, we take chlorine's atomic mass, chlorine-35's atomic mass, which is 34.96885. Okay? And then we multiply that by a fraction. What goes on the bottom of that fraction? Always 100. Okay? And then the top of that fraction is what percentage it shows up to be. So in this case here, we take 75.53 on the top. All we just did there was turn our percentage into a fraction. And then you multiply that out. You end up with like 26 something. What do you get?
26.411.
That's close enough. 26.411. Actually, what's right after the 1? See, I knew that was, yeah, it's like 9, and then there's like a 2, 7, and then there's a 2, right? Okay, all right. So we'll chop it off there. All right, so you got that. You do the same thing for chlorine 37. So you take chlorine 37's atomic mass, which is 36.97790, and then you multiply that by a fraction. What's going in the denominator of that fraction? 100's going on the bottom, right? And then the percentage, or the number, 24.47 goes on the top. And then this one turns out to be like 9 point something. Anyone? What is it? Alright. So you do those two, and then what do you do with those two numbers? Add them together. Guess what you're going to get? 35.45. Good. So, Dunphy said that at the same time that I said it as well. Dunphy, are you just really fast with your math?
No, I just read it off the top.
Ah. How do we check whether we get the right answer or not when we do this?
Table.
Go look at the periodic table and find out what the average atomic mass for chlorine is. So you find the periodic table and you find out that the average atomic mass for chlorine is 35.45. When you add these numbers together, you actually get like 35.46 when you add these numbers together. It's just a rounding thing, right? You know, we're close, okay? Good there, okay? Mora, now's your chance, okay? If you flip your outline that we've been working on back over to the front side. On the front side, we talked about these two charts, and especially this one on the bottom that compared the different isotopes of magnesium to carbon-12. But if you look at that chart a little more closely, see what the third column represents? Oh, natural abundance. If you know the atomic mass of each individual isotope of magnesium, and what percentage each one of those shows up in nature, guess what you can do? Find the average atomic mass. So why don't we do that and find the average atomic mass for magnesium? Let's go through that calculation and find out what we get out of these numbers. Where are you going to check to find out if you got the right answer or not? Find the periodic table and find magnesium on the periodic table. So let's take 2 minutes. You can do that on the side if you want to, or on the back of your outline. There's some space down at the bottom, you know, whatever works for you.
Where do you want us to like round to?
Just do your best, you know. So, usually on the periodic table, most average atomic masses go out to like the second decimal place. That's about where they usually go out to. So, calculate the average atomic mass for magnesium based off of this formula.
So what is the magnesium?
Say again?
What is the magnesium? So I have to count up all those.
So, first, in just making sense as far as the calculation goes, okay? The biggest percentage of isotope that shows up is magnesium 24. Is the average closest to that one's atomic mass? Should it be closest to this one's atomic mass? Real life.
Because the natural abundance is more.
The one that has the biggest percentage of isotopes, right? The average is going to be closest to that one, right? If we took a look at this last table, which is on the back side of your outline, right? For zinc, the average atomic mass should be closest to which one? Go ahead.
It should be the closest to the one on the top.
One on the top, right? Because that's which one shows up the most often, right? Now, in this case, because there's such a wide range, we might not actually see that, but generally it's the case. Okay? All right, we're good there?
Yes.
Why do we do this? Let's talk about that. Okay.
To practice for the test that's going up in about a couple of weeks.
No, actually, that's really not why. So, this is
Make us
this.
model.
Well, yes, but I'm talking about why do we, in terms of science, do this? Okay.
These atoms are important.
Atoms are what?
Important.
Yes, that's true. And more importantly, how many atoms we have becomes important as well. So, let's check out the next outline. Okay? The next outline deals with the idea of quote-unquote counting atoms. But is it possible for us to actually count atoms? It's pretty tough to do, right? But you guys have actually practiced this before. You have come up with a way to quote-unquote count things without actually having to count them. And that was the whole gist of the Bean Lab. The end result of the Bean Lab was you got a mass value that was supposed to represent 300 beans, right? And then you went back and counted. Did you get 300 when you went back and counted? No, you didn't. Does that mean that this doesn't work? No. Why didn't you get 300 when you went and counted the actual beans in the lab last week?
The beans vary.
All those beans are different sizes, right? They're not all the same. So counting out or using the mass values to count out numbers might not get us exactly what we're looking for, but at least in the ballpark, right? And that's the whole gist of the relative mass scale, right? That's what we're talking about in using the mass to help us count stuff. Because, right, atoms are too small for us to really do anything with, right? Here are the actual masses of a proton, a neutron, and an electron. So a proton, right, 1.6765 or 67265, but times 10 to the minus 24th power. Meaning that you have this number, right, but what's in front of it?
24 more digits.
Not 24. It's actually what?
23.
It's actually 23 because we got to move the decimal. We'll talk about that more later this week, right? There are 23 zeros that show up before this. That's not convenient for us to do anything with, right? And that's why we developed this idea of atomic masses, right? So instead of talking about grams, comparing atoms grams to grams, we compare them all in relation to carbon-12. How big is it compared to carbon-12? Is it 2 times as big, 3 times as big, half as big, whatever, right? That becomes a little bit more confusing because our standard carbon-12, we didn't assign that value 1, right? What did we assign as far as the value of carbon-12 goes? What do we call carbon-12 as far as the comparison goes? What number does it get assigned? What is its atomic mass? Christine? 12, right? So we have to talk about it in terms of how big is this carbon atom in relation, or how big is this atom in relation to the number 12, not necessarily to the number 1. Okay? Good there? But what we can do with that is, right, we just went through and calculated the average atomic mass, and that's the number that shows up on the periodic table, okay? For most elements, not all, and there's a reason why some of them aren't, but most elements have that number is the average atomic mass. It's a weighted average. Oh, goodness gracious. It's a weighted average that takes into account the atomic mass of all of our naturally occurring isotopes. Goodness. That part's going to be confusing to watch on the video. So average atomic mass is a weighted average that takes into account the atomic mass of all of those isotopes that exist out there. Okay? But, more importantly, sorry, did we get this part? More importantly, in terms of what it does for us, why is that average atomic mass value important? We went through how to calculate it, but we now need to use that value. Here's why.
I wasn't done with it, man.
I want to get the end of this here. Hold on. Sorry. So, we have set up a relative scale to count atoms based off of carbon-12. Because the atomic mass of carbon-12 is exactly 12, you can take carbon-12 atoms and put them on a scale till it reads exactly 12. And there will be a certain number of atoms on that scale. How many? I'll show you in a second. But that number that gets us to 12 grams of carbon-12 is the standard counting unit, the standard counting number. What was your standard counting number in the Bean Lab? What did you start off with? 100. We based everything off of 100 beans. 100 atoms doesn't get us real far, so we have to use a bigger number than that. And we will introduce that number tomorrow. So tonight, some reading stuff that you have to do. All I want you to do for homework tonight is read these 5 pages. Page 129 through 134, and we'll explain what we're going to do tomorrow in class.